Cool. So just for the sake of everyone who's not over here, and since I just started the recording, deliverables for the second week homework is the two notebooks, one for the explore versus exploit problem, one is the Kelly criterion problem, and the two respective PDFs. So four files you have to submit on Blackboard, okay? And again, 85% of the credits is for the explore versus exploit problem, 15% of the credits for the Kelly criterion problem. So focus on the explore versus exploit problem, try to do that. If you successfully do that, then you get 85% of the credits and you'll be in a good shape. And only after you're done with the explore versus exploit problem, you can move on to the Kelly criterion problem, but not before that, okay? Any questions before I move on? Okay. So since this is an office hour, so rather than me just going over the problems, I would like some of you to ask me some questions where you got stuck or where you had a problem understanding. So that's going to make the session a little more interactive, and I believe it's going to help out everything stuff. Me just reading through the problem and none of you getting what's going on. So did any of you take a look at the homework, like or the multi-arm bandit problem?
Yeah.
Okay, so where exactly? Can someone tell me where exactly was the confusion? Was it understanding what the function blocks were doing in the starter code, or was it the objective for the homework? Like, what do you have to do for the homework? Where exactly was the confusion?
Yeah, can we go through some of the blocks of code?
Sure, sure. That's totally fine. So I'm going to start with the explore versus exploit problem, and then move on to the Kelly criterion if time permits. Let me share my screen. Right. Cool. You guys can see my screen, right?
Yeah.
Okay. So the multi-arm bandit problem. So like I described last week, it's a combinatorial problem. It's a reinforcement learning problem, if you may. So the problem on the face of it is not very complicated. So here you walk into a casino, and you have these M slot machines in front of you, and each slot machine has a probability of winning. But the deal is you don't know what the probability of winning on each machine is, right? Now, obviously, when you walk into a casino, you would want to win some money, right? So you walk in with some cash in your pocket, and your goal is to play a round of a slot machine and maximize your wealth. Now, let's suppose that you are told that you can use a maximum of n pulls, a capital N pulls, okay? Which means that out of all the M slot machines, you go on pulling all the slot handles on all the slot machines up to n times, okay? So once you reach n, you're done. Your game is over. Any questions up to this point? So you have M slot machines, and you have total of n pulls that you can use to maximize your wealth, or just play a round of the game. Does this make sense?
Yeah.
Okay. So the question over here is, how do you find out which machine has the highest probability of winning? Okay, because if you want to maximize your wealth, you would want to know which machine gives me the best bang for the buck. So you have to identify that machine. Once you identify that machine, then you keep playing on that machine until you reach the number n, or you reach the total number of pulls. Okay, so that is sort of the bigger picture of the multi-arm bandit problem. Now, in explore versus exploit, as the name suggests, in the explore phase of the game, you find out, or you try to estimate which machine is the best, okay? And how do you do that? So let's say I give you, or rather I tell you that out of the n total pulls, use k pulls on each machine, or k trial pulls on each machine without betting any money during this period, to find out which machine has the highest probability of winning. Does that make sense? So I give you total of n pulls, and now I tell you that I'm going to give you k trials or k trial pulls on each machine to find out which machine has the highest probability of winning. Okay, make sense? So the goal is, how do you find out what is the optimal value of k? So here's the deal, right? So if your trial, let's say you have 5 machines, okay? And I tell you that, and I give you, let's say, 100 pulls, okay? Now I tell you that the total number of trial pulls that you can use on each machine is 2, okay? So you have 5 machines, total number. So for the first machine, you can use 2 trials to find out if it has the highest probability of winning. For the second machine, again, 2 trials. Third machine, 2 trials, and so on and so forth. Now, take note that if it's just 2 trials, well, the only possible, so if it's a two dimension or just a area of size 2, the only possible values you can get are 1, 0, 0, 1, 1, 1, or 0, 0, right? Yes or no?
Yeah.
Okay. So your 1 is a, if you win, that's a 1. If it's a 0, you lose. Okay. So your 1, 0, 0, 0, 0, 1, and 1, 1. Okay. And that is true for all the machines. Now, it's very intuitive to understand that if your number of trials is low, then your chances of estimating which machine is the best goes down. So you only have 4 options, then it may so happen that the wrong machine or a machine with a lower probability of winning may give you a 1, 1, and a machine which is actually the best one out there gives you a probability of 0, 1. So you're going to wrongly estimate the machine, right? So and take another scenario where, let's say, out of on the 100 polls, I'll tell you that, okay, use 90 trials on each machine. Or 90 trials on each, I'm sorry, 10 trials on each machine to find out, or let's say, how many machines do I have? 5 machines, 100 trials. Let's say 9 trials on each machine. 9 trials on each machine to find out which is the best. So out of the 100 trials, I reserve 9 times 5, that is 45 trials to sort of estimate which machine is the best. Now that leaves me with just 55 polls. Now that might not be enough to maximize my wealth. So there is this number between 0 and 100. We have to find the optimal number k so that I don't waste too many of my polls in estimating, and I don't use too less of a number for k so that my estimation is wrong or close to the wrong. Does that make sense? Yes or no?
Yeah, it makes sense.
Okay. Somebody let me up to the chat head. Okay. Yes, I'll come to the plotting thing, Timothy, in a second. So once you have that, once you find out which machine, or you have estimated, don't make sure when I say finding out, that means we're estimating. Even when we're estimating, we are not sure if that machine is the best one or not. So that is where the objective of this problem comes in. So what you have to do for this problem is that you have to estimate, or you have to plot the fraction of your wealth achieved by taking, so what is a fraction? So fraction is the wealth that you've achieved by estimating that a machine is best, divided by where your denominator is the wealth that you could have achieved by knowing which machine is the best. So let's say you walk into the casino, I tell you, okay, here are the probabilities of winning on each machine. So the first machine has a probability of winning 0.1, the second machine has a probability of winning 0.5, so on and so forth. So you know a priori, you know beforehand which machine is the best. So you can just walk up to the machine and just start playing your game and maximize your wealth, I mean, as much as you want, unless you reach the total number of pulls, right? But here's the deal. I don't tell you what the probabilities of winning are. You're estimating it. How do you estimate it? You go to each machine, pull the slot machine handle k times, and you get a series of 1s and 0s. Right? You get an array which consists of 1s and 0s. Now you take a look at all the arrays of all the machines, and you find out which machine has the maximum number of 1s or the maximum number of winning streak, right? And you say, okay, so I feel this machine has a maximum number of winning streaks, so this might possibly be the best machine out here. So you start playing your game on that. So again, the fraction of wealth is the wealth that you have achieved by playing on the machine that you have estimated to be the best, divided by the wealth that you could have achieved by knowing which machine is actually the best, okay? So that is your y-axis. Your y-axis is the fraction of your wealth that you have achieved, and your x-axis is the total number of pulls, okay? So you vary your total number of pulls, and what you would see is that as you increase the total number of pulls, your fraction of wealth achieved is gonna go up. It's sort of like an exponential curve. If you let me show you. So let me share my screen. Right. Okay. Here is one example. This is using Kelly criterion though, but this is gonna make sure that you get the idea. On the x-axis, as we said, we have the number of pulls. So the number of times you get to pull the handle on the slot machines in total, you're increasing that on the x-axis. On the y-axis, we have the wealth growth rate, or the fraction of wealth, okay? And as expected, intuitively, if you think of it, if I give you more chances to play the game, your chance of accumulating money goes up, right? That is very intuitive. If I give you more number of times to play, then you can just keep on pulling the slot machine until you get a certain amount of money. So that is obvious. So you're with increasing the number of pulls, your fraction of wealth achieved is going to go up. Okay, does that make sense? Yes or no?
Yeah, it makes sense.
Okay, cool. Okay, now before I move on to the objective again, I'll briefly go through the function blocks. The function block, first one is pull arm. So what it does is you walk up to a machine. Yeah, sorry. Did someone say anything? All right, okay. So first one is the pull arm function, where you basically walk up to a machine and basically pull the arm of the machine n times. So what you get is an array of size n, okay? So let's say I tell you the probability of winning on each machine is, let's say you walk up to a machine and I tell you the probability of winning on this machine is 0.5, okay? And I tell you that you can pull the trial number of, the maximum number of trial pulls on this machine is 6, okay? So the k is equal to 6. So what you basically get is an array of size 6, where each element in an array is either 0 or 1. So if it's a 50%, if it has a 50% probability of winning, so what you would expect to see is 3 ones and 3 zeros, right? Half win and half loss, right? So that is what this function block is doing. It takes in the probability of winning on a machine and gives you an array of size n, where the element of the arrays are the number of times you win or lose. That is basically ones and zeros, okay? Make sense?
Can you repeat it real quick?
No.
Okay, again. This is for a single machine. This function block is for a single machine. What does it take as an input? The probability of winning on that machine, and n is the number of pulls that you would want on that machine, okay? Does the input make sense? So you're taking the probability of winning on that machine and the number of pulls on that machine. That is your input to this function block. So you walk up to a machine and I tell you, let's say, I tell you that the probability of winning on this machine that you're standing in front of right now has a probability of winning 50%, okay? P is equal to 0.5, all right? And I tell you, you can use 10 pulls on this machine, that is n is equal to 10. Is that making sense? So P is 0.5 and n is equal to 10.
That makes sense.
What this function is gonna return is an array of size 10, okay? What are the elements of the array? It can be either 1 or 0. So you basically would have 1, 0, 0, 1, 1, something like that, where the total size of the array is 10. Now, if a machine has a probability of winning 0.5 or 50% chance of winning, what is the possible number of ones and zeros you would likely see in that array of size 10?
5 ones, 5 zeros.
Exactly. So you have 5 instances of winning and 5 instances of losing. That's what you would see. This is exactly what this function is doing. It's taking in your probability of winning on a machine. It's taking in the number of pulls you would want to have on a machine, and it gives you a set of values where certain number of values are your winning combination, and certain number is your losing combination. So you have a random number of ones and zeros. Okay. So what is the bigger picture here? You go to each machine and you run this function on each machine, and you get this array of ones and zeros for each one of the machine. And basically, you check which array in which machine has the highest number of ones. Okay. So what does highest number of ones mean? It means that it has the highest possibility of winning. Again, what does this do? You take this function and you go to each machine and run this function. Okay. What this is going to give you is an array for each one of the machines. Now you look through the arrays. Okay, so the machine 1 has 4 ones. Machine 2 has 2 ones. Machine 3 has 6 ones. So you basically lock on machine 3 because it has 6 ones of the highest probability of winning, or you estimate of highest probability of winning. Does that make sense?
Yeah, that makes sense.
Okay, great. This create MAB function is exactly what I told you right now. It takes in M, where small m is your number of machines, n is your total number of pulls, okay? P is a random, it's a vector of size m, or an array of size m, and each element of the array P is a probability of winning on each machine, okay? So let's say you have 5 machines, P gives you an array of size 5, where each element in this array is a probability of winning on a particular machine. So the first element is the probability of winning on first machine. The second element is the probability of winning on second machine, and so on and so forth. np.random.uniform yes, I was coming to that, sorry. np.random.uniform means you're basically uniformly picking a number between 0 and 1. So 0 is a lower limit, 1 is your upper limit. It's a uniform distribution where you're randomly picking a number from 0 to 1. Are you guys familiar with uniform distribution?
Kind of, but not really.
Okay, so what does uniform distribution mean? That if I tell you that you have some numbers distributed uniformly between the lower limit A and an upper limit B, and any number between A and B is equiprobable, which means that the probability of picking any number between A and B is equal. Does that make sense?
Yeah, that makes sense.
That makes sense.
Okay. All right, so this is what this vector P is doing. What is this capital M? This capital M is a matrix. It's a matrix of size m cross n. You have m rows and n columns. So basically, what is this? This matrix, where your each row is the array returned by this function, okay? So each row of this matrix M is the array returned by this function. That's why you have n columns. Yep. So each row of your matrix capital M is an array returned by this function. So how many rows are going to have? The number of machines that you have. So you have small m rows, that is the number of machines, and each row in your matrix is the winning streak or this array returned by this function full arm. That is exactly what it's doing. You're making an array or making a matrix where you're taking in this function full arm that's going to give you an array, and you're taking that array and putting it in the first position of matrix M, okay? And then you take the second element of the array and put it in the second position of the matrix, so on and so forth. So you have an m cross n matrix. Make sense?
Mm-hmm.
Okay. Play A may B. So this is taking in 3 functions: total, the number of machines that you have, total number of pulls that you can use, and T is the number of trial pulls on each machine, okay? This number T is something that we're going to determine later on, okay? So again, what are the inputs? Number of machines, number of total pulls, number of trial pulls, okay? So basically, you go ahead and create an instance of your problem using the total number of machines, the total number of pulls. What is it going to give you? It's going to give you this probability matrix P from this function P, and this matrix M, these are your return arguments, okay? Once you have that, then you go ahead and find out the optimal number of trial polls that you're going to use in the explore phase. Again, remember, during the explore phase, we are not betting any money. We're just trying to find out, or we're just trying to estimate which machine could be the best, okay? So this is what we are doing over here. We are taking in number of machines, the total number of polls, and the possible number of trial polls that we would want to use. This T over here is an upper bound to the number of trial polls that we would want on each machine, okay? So again, this is an upper bound. This is not exactly the number that we might want. That depends on this explore MAB function. So what is the actual number of trial polls? That is K, okay? Is that making sense?
Is that T something that we decide, or is that something that gets calculated?
T is something that you decide. So that when you plot your function, you're going to vary T and see as you increase your T, how does your plot change, okay?
Gotcha.
All right. So let's move on to explore MAB function, because the other parts won't make sense otherwise. So okay, explore MAB. What does it take as input? The number of machines, the total number of polls, the upper bound on the trial polls that I've set, that is T, okay? What do we have to do? We have to compute the optimal number of trials K, which is obviously less than my upper bound of each arm given n polls, okay? Make sense? Yes or no?
Yeah.
Okay, great. Excuse me. Now, if you're, okay, let's say you have, excuse me. So let's say you have n total number of n polls, m machines, and obviously your m is always going to be less than n. If your m is greater than n, it doesn't make sense, right? So if your number of polls is less than your number of machines, then it doesn't make sense of playing the game. So obviously your number of polls have to be always greater than the number of machines that you have, okay? Now what do? If your average number of polls on each machine, what is the average number of polls? The total number of polls divided by the number of machines. Again, if your average number of polls on each machine or average number of trial polls on each machine is less than the upper bound, T, then the number of trial polls that you use during the explore phase is basically the average number of trials. That's what it's doing. If that is not the case, then you assign the upper bound that you've set for the trial polls. Make sense? So again, you have set an upper bound T that you would want to use at most on each machine during the explore phase, okay? No matter what, you won't go over T, okay? Now what you do is that you go ahead and find out the average number of polls on each machine. What is the average number of polls? The total number of polls that you have divided by the total number of machines that you have. If the average number of polls is less than the upper bound that you have set for each machine, then you know for a fact, okay, so by pulling some number less than T, I can still have an estimate because the average number of polls is less than my upper bound that I've set for each machine, right? So if that is the case, then I'm returning, or basically the number of polls that I'm going to have on each machine is the average number of polls, that is n over n. If n over n, or if the average number of polls is not less than T, or if it's greater than T, then the number of trial polls on each machine is going to be equal to T, or the upper bound that I've set. Does this make sense?
Yeah.
Zohar, did that make sense, Zohar? Okay. All right, now going back to this function, what we are doing is we are finding this optimal number of trial polls that we're going to use in the explore phase, that is K. Now, here's how we analyze this. So take a look at these two lines of code. Overview. What these two lines of code is doing is basically estimating your fraction of wealth by, I'm sorry, it's creating an array of your fraction of wealth by playing on the machine that you've estimated to be the best, okay? What this W estimate is doing, it's basically estimating your wealth and A estimate is basically trying to estimate which machine could be the best. Okay, so these two lines of code, what is this doing? I'm sorry. I'm sorry. These three lines of code. So your W estimate is an array that you create to uh, to store the fraction of well that you've achieved by estimating which machine could be the best. A estimate is the index of the machine that you think is the best. So when you return an array and you find out the array with the maximum number of ones, that index of that array or the index of the machine which has the maximum number of ones is given by A estimate. Once you have this A estimate and you create this vector W estimate, you basically now keep on playing on that machine until you run out of n, okay? Or you run out of total number of code. These three blocks of code is for one instance of a problem where you're trying to find out the wealth that you have achieved by estimating which machine could have been the best. Does this make sense or not?
That makes sense.
Okay. Now focus on these two lines of code.
Can I ask a question about those previous lines? I'm a bit confused about for example, when you're calculating WS, where are you getting that A times K?
Where am I getting this A times K? Okay.
Yeah,
So basically what is happening over here is you start with, so what is A times K? A basically number of trial poles, right? So A you can consider M. So look at this. For A in range of M, so let's say M is equal to 5, right? So what are the iterations of this for loop? 1, 2, 3, 4, and 5. So you start with 1, and you pull the handle on the first machine K times, go to the second machine, now A is equal to 2, now you go to the second machine and you pull the handle K times, right? So on and so forth. So basically, W estimate is trying to find out, or it's giving you a wealth that you could have achieved by, so at this point, what W estimate is returning, it's basically the matrix M. So you have this matrix M, which is of size M cross N, and it gives you for each row of the matrix, it's the number of wins or loss on each machine. Does that make sense?
yeah.
Okay. Okay, so again, W estimate at this point, I'm sorry, W estimate at this point is giving you a vector. Okay, can I write somewhere? So what is, let's see. W estimate is basically a vector like this, where 2, 3, 4, 5, 6. Okay, let's say this is what you get by W estimate. It means on the machine you have 2 wins. On the second machine you have 3 wins. On the third machine you have 4 wins. On the fourth machine you have 5 wins, and on the fifth machine you have 6 wins. Okay, this is what a W estimate is going to look like. So it's basically taking each one of the array of each machine and he's summing up the number of ones on that. Okay.
One thing I'm confused about is why is the number of wins for a machine correlated to its index in M?
Why?
Like.
Okay. So here's the thing, right? So you're taking this matrix M, right? And what are you trying to find out? You're trying to find out the number of wins or loss only during the explore phase, right? So your explore phase, you're pulling the handle on each machine K times, right? So you get that one streak of wins and loss on each machine by pulling, so you have an array of size K. So basically what, at this point, the size of the matrix M is M cross K, okay?
Mm-hmm.
So each row of your array is the vector of the explore phase. What you're trying to find out is the number of ones on each machine. And basically you're summing over up. So np.sum is basically summing over number of ones in each row of the matrix. Does that make sense?
Yes, sort of. I'm just like, the way I'm thinking about it is that with the way this is going. Oh wait. So M is capital M a matrix?
Yeah, capital M is the matrix.
Is each index of M its own like list?
Right,
Like
exactly. So each index
okay,
of the machine,
okay, I
M,
see.
capital M is your machine index, and each row of your of the matrix is the number of
Okay,
on the
I understand. Thank you.
All right. Now a estimate, excuse me, a estimate is giving you the index of the machine. So what is your matrix M now? Your matrix M now is a M cross K, M rows. So each row index is a machine index, and each column is the number of, or each row is the total row of the matrix for each one of the total number of elements in each row of the matrix is your number of wins and loses, right? A estimate is basically taking in this W estimate, right? Let's say I take in this example of the W estimate. What is it going to do? It's going to find out the index of the element which is highest. So over here, my fifth element is the highest, which means my estimate is that the fifth machine is the best right now because I have the highest number of wins on that machine. Okay, that's exactly what it's doing. You're taking in the array W estimate, and you're trying to find out the index where you have the maximum, the highest element in that array W estimate, right? np.where takes in the argument where I want to find out the index, the largest element in that array, and I'm returning that index to A estimate. Okay, so A estimate holds the index of the machine that I've estimated to be the best. Make sense?
Why is there a 0 at the end there?
Oh, that is basically so when you call it np.where, it's basically returns a list of lists.
Okay, that makes sense. Thank you.
All right. Now what I'm doing with the rest of the pulls that is left to me, how many pulls I'm left with? M times k to n, right? So if you have total number of n pulls and you're pulling during the explore phase, if you're pulling k times on each machine, so you're wasting m times k explore pulls in total, right? So the total number of pulls that I'm left with to maximize my wealth is n minus m times k, right? So that is exactly what we're doing. Now we are starting to play the game. Now at this point, we are starting to bet money, real money on that. So we have estimated which machine is the best. We are taking that index of the machine, and now I'm going to play the rest of my pulls on that machine. Okay? Make sense? All of this? Okay. Now over here, what are we doing? A best, this is the index of the machine, which is actually the best. So I'm taking in the probability of winning on each machine, and I'm finding out for real which machine is actually the best. Make sense? This is my estimate of which machine could be the best. This is the actual index of the machine, which is the best. This and this may not be equal. That is the deal. If they were equal, if we knew for a fact that these two were always equal, then we didn't have to play the game, right? That is the deal. This is always the index of the machine that is the best for sure. This is the index of the machine that we think could be the best, okay? So once we find out the index of the machine that is actually the best, we play we find out the total number of, or we try to maximize our wealth on that machine, okay? So this is more like an imaginary situation. What if we knew which machine is the best? And what if we knew the best machine, what is the total money that we could have possibly accumulated by knowing which machine is the best, okay? This is what we are winning for real. This is the actual scenario. So we don't know which machine. I think this machine is the best. I go up there, pull the explore polls, and okay, this machine has possibly the best chance of winning, so I'm going to play on this machine. This is a what if scenario. What if I knew that machine, the fourth machine is the best? I come into the casino and I'm told, okay, you walk up to the fourth machine that has the best chance of winning. You play your money on that, and you come out as a millionaire. Okay, this is the what if scenario. What are we returning in this function block is basically this fraction, this fraction of wealth that we have achieved by playing on a machine that we think is the best over the what if scenario. Make sense? That is the fraction of wealth. That is what we are plotting over here or here for that matter. This is the fraction of wealth, or let's say this is a better estimate. This is the fraction of wealth. The fraction of wealth is basically the wealth that I've achieved by playing on a machine that I think is the best over the wealth that I could have achieved by playing on the machine that is surely the best.
But so this is an array of fractions, correct?
It's an array of fractions, exactly. Yes.
Okay.
Make sense? Okay. Now, what this function block is doing is basically you're playing this game capital N times. You're playing this game over and over and over again to get it. Are you guys familiar with the Monte Carlo simulation by any means? Have you heard of Monte Carlo simulations?
I don't think so.
Okay, so it's a very simple idea. If you, let's say a coin toss, okay? You want to get an estimate if that coin is fair or not, okay? You guys are familiar with the term fair coin, right? Yes or no? Probability, any
Yeah.
class? Okay. I'm trying to find out if this coin is fair or not. So if you just toss it once, your chance of knowing if it's a fair coin or not is 50%, right? Half. Now, let's suppose you keep on tossing it over and over and over again, and you get, let's say you toss it for 100 times, all right? The number of times your coin lands on head, let's say that is 70 out of 100, right? Now you have a better estimate of knowing, okay, so this might not be a fair coin because I get more number of heads than the number of tails, right? So basically, as you increase your number of trials, your chance of estimating whether some function that you're trying to find out is biased or not biased, okay? Does that make sense?
Yes.
Okay, this is exactly what we're doing. We're going to play this game over and over and over again to understand which machine is actually the best, or we are trying to find out over and over and over again what is the total maximum wealth, or the maximum fraction of wealth that we could have achieved. How do we do this? We play this game, let's say 1,000 times, and we basically find the average of that, okay? This is exactly what this function block is doing. You play this game 1,000 times or 10,000 times or 1,000,000 times, your wish, and you basically take the average of that. That's what this function block is doing. All of this make sense?
Yes.
Yeah.
Awesome. Okay, now to the real part. What is that you have to do for the homework? What you have to do for the homework is basically plot an instance of your problem, which would look like this or this. Let's talk about this one first, okay? This is a function plot of the number of polls versus the fraction of maximum wealth achieved, where I just have two machines, m is equal to 2. And the total number of times I'm playing the game is just once. And as expected, if you just play the game once, or if you just toss your coin once, you're going to get a terrible estimate of the total fraction of wealth that you could have achieved, right? I'm just tossing the coin once, and the chances of landing on heads or tails is just 50%. So I don't know. It like from one trial, it looked to me that it's fair coin, but it may so happen that if I keep on tossing, I would get all 90 of them heads and just 10 of them tails, right? So the lower your number of trials, or the lower your number of times you play the game, the worse your estimate is going to be. So it's always suggested that you play the game over and over again. So a good number could be 1,000. N is equal to 1,000. You play the game 1,000 times, okay? Anyway, so what do we have over here? On the x-axis, we have the number of polls. On the y-axis, we have the fraction of maximum wealth achieved. And the different plots that you see is that we are varying the total number of, or we are varying the upper bound on the explore pools we want on each machine. So this blue line, if you see, that is just for one explore pool on each machine. That is a terrible estimate. Okay, you would never want to pull the handle on each machine once to find out if it's a win or a loss, because it's a binary. It's a 1 or a 0. So you would have multiple machines winning or losing, right? Make sense?
Yeah.
Okay. And then you keep on increasing the number of explore pools that you would want at most on each machine. As you keep on increasing the number of pools, let's take a look at t equals 32. I'm sorry. Okay. t equal to 32 and t equal to 2, okay? This orange plot and the sort of brown plot, okay? Look at the orange plot. This is going
Oh
up.
wait, Avinanda, we can't see what screen you're showing.
Oh, you can see my screen? Resume share. Hold on. Just hold on. Right. Can you guys see it now?
Yeah.
Yeah.
Okay.
Yeah.
All right. I'm sorry. So again, on the x-axis, you have the number of polls. On the y-axis, you have the fractional wealth achieved. How many machines am I using over here? 2 machines. And how many times am I playing the game? Just once. Like I said, if you play the game once, you're gonna have a terrible estimate of your fractional wealth achieved, right? Okay. Now what am I doing over here? The different colored plots that you see, or the different colored graphs that you see, is for the different value of t that I'm choosing. Okay. So t equal to 1 means I want to pull the slot on each machine once to find out if it has the best probability of winning. And that is a terrible thing to do. Like if you pull the slot once, it's a binary number. It's either 1 or 0. And if you have like 100 machines, like multiple of them are going to have 1s and multiple of them are going to have 0. So you can't even estimate, right? Does that make sense?
I think so, yeah.
Okay, great. Now what I'm doing is I'm slowly increasing the number of explore polls that I would want to have on each machine at the most, okay? So let's take a look at t equal to 2 and t equal to 32. That is this orange one and this brown one. If we take a look at the orange plot, look at how much like disturbance this plot has. It gives you a terrible estimate of how your fraction of wealth is increasing over time, right? Now look at the brown one, t equal to 32. If we take a close look, this has a sort of increasing trend. It gives you a better estimate of the fraction of wealth achieved. Look at that. It's going up slowly, and then it sort of saturates at this point. Does this make sense?
One thing I'm sort of confused about is, are we not varying small n?
Yes, you're varying small n as well. Your x-axis is small n.
Oh, I see. Okay.
Your x-axis is small n. Your
Yeah.
y-axis is your fraction of maximum wealth achieved. And
Uh-huh.
what are you doing? You're plotting different instances of t.
Okay. But the number, they all will go up to 600.
Yes, all will go up to 600.
Okay,
Yes.
I see.
Does this make sense to everyone? Why? Let me look at. Are you showing us something? Why is the fraction of maximum wealth achieved higher than 1 at the start of the blue plot? Okay, start of the blue plot, that is t equal to 1. Oh, okay. To answer your questions, O'Hare, here's the deal. Just let me take a look. If you toss a coin once to find out if it's a fair or not, what are your chances of knowing if it's fair or not?
50.
Right. So if it's 50, then you know what is the estimate going to be? Is it fair or is it unfair? Why do you say unfair? What is a fair coin? A fair coin is a coin which has 50% chance of winning and 50% chance of losing. So you toss it once and you find out, oh, I landed on tails, which means like I have 50% chance of losing, which means I have 50% chance of winning. So it's a fair coin. That is exactly what is happening over here. It makes sense, all right?
Yeah, I have a quick, I don't know, I don't want to derail what we're talking about.
Sure, yeah.
But I have a quick question about Explore Map. When you were talking about what it returns,
Mhm.
how are we returning? So you're talking it's a fraction of arrays, correct?
Just let me go back to the code. Right, you were talking about the explore map function, right?
Yeah. So it says it returns a number of poles of each arm.
Yes, no, what it returns, yes, that's true. This number is constant for each number. So this number k or number t, whatever you choose,
Yeah.
this is going to be the same for each arm.
But so why do we care? Why do we care about how many times it pulled for each explore polls of each arm?
Why do we care? Okay, good question. Again, this goes back to this argument that I started with. that let's say you have 100 pulls in total, okay?
Yeah.
And I tell you, okay, you can pull or you can explore once on each machine. That you can pull the handle on each machine once to find out if it has the highest chance of winning or losing, okay?
Okay. Yep.
Now, let's say you have 10 machines, and if you just pull the slot on once, and it would give you a binary number, right? A 1 or a
Yeah.
0. So you
Yeah.
would have, like, let's say 6 machines giving you a 1 and 4 machines giving you a 0. How would
Okay.
you find out which machine is the best one? And now let's say you have 10 machines, and I tell you that, and you have a total of 100 pulls,
Mm-hmm.
and I tell you that, okay, go ahead and use, how many machines do I have? I have 10 machines and 100 pulls. So let's say I reserve 7 pulls on each machine, okay?
Okay. Yeah.
7 pulls on each machine, just
So
for exploring.
So you said there's if there's 70. So in total,
70,
it'd be
exactly.
70.
So you're wasting 70 of your 100 pulls and just finding out which machine is the best.
Okay. Okay.
And that leaves you with a very small amount of actual pulls to like maximize your wealth.
Yeah. So we're only calling explore map in the function to find. We're not.
Yes,
we're
just
not,
over here.
Yeah, we're not using it in the main function whatsoever.
And not even over here, and not even when you call the main function block. No.
Okay.
So just you're finding out the explore map only during when you're creating an instance or playing just one round of the game. All right.
Yeah, but we have to call multiple of these functions in the main block to get
Right,
everything
exactly.
to work.
You have to
Yeah.
call it multiple times. Yes.
Okay.
All right. Does that make sense? What do you have to do for the homework now? Ethan, do we want to vary n in a plot to something greater than 1? Yes. To answer your question, Ethan, and for everyone out here, your capital N, that is, just let me again stop and I'm sorry, my Zoom is a little messy right now. I don't know why. Okay. So this N should always be a large number. You would want to play this multi-armed bandit game over and over and over again to get a better estimate of your plot. Let me give you an example of what I'm talking about here. Let's say, let's take a look at this plot. Hold on. What's happening here? Share. Oh, what the hell? Can you guys see this? Can you guys see this? This blue.
Yeah.
Okay, cool. Look at this. This has n is equal to 100. Okay. I'm playing this multi-arm bandit game 100 times now, and if you take a closer look, this is with m equal to 2 and t is just equal to 1. Compared to t equal to 1 over here, take a look at the t equal to 1 plot over here. This blue line. This is almost just a line with just disturbances and noise, right? It doesn't give you an estimate. It's not increasing. It's not decreasing. It's just a random line with just fluctuations, right? That is for n equal to 1. Compared to this, I again have t equal to 1, but now I'm playing 100 rounds of this game. If you take a look, this has sort of an increasing trend over here, okay? And trust me, if you make this 1,000, this is going to be a much more clearer increasing trend. And if you make it 10,000, then it's going to be way better than what you would expect, okay? Does that make sense?
So for our homework, we're basically taking and plotting, varying into some very large number, and then plotting multiple different lines which vary with the number of explore polls, and we're plotting those all on. Okay, okay, that makes a lot of sense.
Okay.
And
yes, go on. Sorry.
Is there, like, in order to, like, you know, because it does take so long to process, for the maximum number of explore polls that we want to set, should that be some type of like fractional value of our number of polls or something, like, or like, how should we do that if I run, like, you know,
so
10,000
trials, total number of explore polls always has to be an integer. It has to be an integer because you can't pull the handle on each machine, which is a fraction, right? So it can be 5.5. So what does 5.5 mean? You pull that 5 times, and what is a half? There is no half over here, right? Either has to be 5 or 6.
I mean, like, out of, if I were to run, let's say, like, if my maximum number of polls that I'm given per machine, let's say, you know, is like I don't know, like 25,
Mm-hmm.
should my explore polls, my maximum number of explore polls be like, a fifth of my maximum number of polls? Or do I just randomly assign however many upper bound of my
Yeah,
explore
so
polls?
if I go back over here, so here's what is happening, right? So let's say you choose, so let's take your example. You said you want your maximum number of explore polls on each machine, you want it to be 5, t equal to 5. Is that what you want?
Sure, yeah.
Okay, so let's suppose t is equal to 5, okay? Now, let's say you have 100 pulls and 10 machines, okay? Easy example. Now, what is the average number of pulls on each machine? That is 100 over 10, right? That is 10 pulls on each machine, right?
Right.
Okay, so 10 pulls on each machine, but 10 is greater than
Yo, Anikaka.
so 10 is greater than the upper bound on the explore pull that you've set aside for each machine, right? So your T is equal to 5, but your average number of pulls is telling you that 10 trials are needed, right? If that is the case, then you go ahead and assign 5 pulls on each machine. So either it's your upper bound or it is the average number of pulls on each machine, depending on which one is lower.
Okay.
I'm sorry. Sorry, I didn't mean to cut you off.
You go, Lev. What's up?
So I'm having a little bit of trouble understanding the use of the variable fset.
Fset. Oh,
It's-
okay. So it's not a variable. Fset is the function. It's an array of the fractional wealth
Mhm.
that you get by running an instance for problem. It's not an input. It's an output.
Okay, so I see. So in the first in that box that you have your mouse over right now,
Mhm.
when we call like the plot function, we're going to be plotting f in fset.
No, you're just going to be plotting fset because fset is an array of fractional.
Oh, I see. Okay, we're going to be plotting fset, and will fset be calculated in that same box then?
Yes, fset is going to be calculated. So what is happening in this block is you're calling all these functions that you have, right? So what you're going to call is this function play MAB, right? That's what you're going to call in this function block. What are the inputs to the play MAB average? That is the number of machines, the number of times you want to play the game, the total number of pulls that you want, the total number of explore pulls that you want, and when you run this is going to give you an array of the fractional wealth achieved, and you just plot against this array and set. That's what it is.
I thought the fset was created by play at mab average.
Yes, it's created by playing mab average.
Okay.
So I'm sorry. Is fset a two-dimensional array? Because
no, it's a single dimensional array.
Okay, well then wouldn't you need multiple fsets for each?
You need multiple fsets for each value of t.
Okay.
So that actually goes in my question about the zip. So when we're plotting it and we use zip function, you have it. You say it says right there, use zip to allow labels for each value of t. So we use t set for the first value that's going to be running through t.
Right.
And what's the second value? Is that going to be fsets?
That's going to be your end set. So you have 2 for loops, right? One is you're looping through the number of pulls, and the second loop is going to be looping through the number of t set. That's going to give you these different colored plots.
Okay.
Make sense?
Thank you. Yep. Thank you.
All right.
One more question about that. When if you're doing every single what's it called? If you're doing every single trial of this essentially with the same n.
So you mean n, small n or capital N?
Small n.
Okay.
So if you have the same number of max polls total for each trial, then wouldn't you not be? I'm just. Wouldn't you want to be looping through n set and t set separately because?
Okay, here's the thing. If you want, you can do that. It's totally fine. How you plot it, how you loop through these values of n and t, that's totally up to you. I mean, if you want, you can use the sort of like the conjunctive for loops where you use for loops together. But if it's easier for you to like loop through, like define like how you do in a C program, you for loop and then another for loop inside it, that's totally fine. I'm fine with that. Okay. But what did that answer your question? Was that the question?
I'm just sort of confused about if you were to do, for instance, for n comma t in zip n set t set.
Sorry, can you come over again?
So you're saying that you could do though, like for instance, for n comma t in zip and set t set.
Mm-hmm.
I'm just a little bit confused about that works, but
I
I
mean,
don't.
look, okay, so if you're having confusion in using zip command, you can just use for
Okay.
for I in range M or N, okay, and then
Okay.
for J in range T set, that kind of thing. You can do that.
Okay. Okay.
Does that make sense? Yeah, go on.
I have one additional question. So what do we vary for the Kelly Curion thing that we're changing? Are we varying what do we change for that? Is that our betting
I'm sorry,
amount?
varying for what?
The Kelly
So
criterion.
the Kelly,
Kelly criterion.
criterion.
Okay. Kelly criterion. Okay. Let me just quickly share my screen. Right. Okay, can you see my screen?
Yes.
On the x-axis, you still have the number of pulls. On the y-axis, instead of now fraction of weld, what you have is a weld growth rate. Okay. So for the Kelly criterion problem, actually, what you guys have to do is find out. Let me just. Can you? No, hold on. What's up with my machine? For the Kelly criterion problem, right? Well, the Kelly criterion problem, what you guys have to do is, so you're given all the function of the plot and everything, right? What you have to do is just find out this, or write this from this function estimate multi-arm bandit, where you're trying to find out estimate the number of pulls on each machine. That's what you have to do. So we are providing you with the plot function as well for the Kelly criterion.
Great. Thanks so much.
Okay. Any more questions? Let me look at the chat box. You all good? Okay, great. I'm ending the meeting then. Best of luck, and do reach out to me if you have any questions. And you have the other TA, Mike Gann. You can reach out to him as well. Yes, question?
How can we access this recording?
I'm gonna stop this recording, and I would either put a YouTube link or a Google Drive. It depends on which one is easier.
Okay, thank you.
All right. Great.